Okay, why don't we get started? It's 2 minutes after the hour, and there's a lot of people in the room right now. So welcome, everybody. We're really excited to have you all here with this update on investigating PFAS in Canadian water systems. This is a project that we are helping to support with the Ontario Water Consortium. I'm Rahim Kanji, by the way, the Executive Director of the Ontario Water Consortium. And we first started talking about this project a couple of years ago with a kickoff meeting, and then we had a follow-up webinar last year to help disseminate the progress of this research that's happening. And so a little bit of background, in April 2021, the Canadian federal government issued a notice of intent to address the broad class of PFAS substances. And this prompted a collaborative effort to investigate and address the presence of PFAS in water systems. So PFAS, of course, is an emerging environmental contaminant which poses significant challenges due to their unknown human health effects. And the ineffectiveness of traditional treatment methods. So we have Professor Hopkins from the University of Waterloo and Professor Berruti from Western University spearheading this research initiative. They've partnered with organizations such as USP Technologies, Brown and Caldwell, the Ontario Clean Water Agency, and several regional water supply systems in Ontario and others, of course, with the aim of mitigating the impacts of PFAS on water supplies. So this project has been supported by NSERC Alliance, the Option 2 grant, and really exemplifies collaborative research really at its best. This grant is a premier grant. They're hard to get, and the Alliance grants really help foster these types of partnerships between university researchers and organizations across sectors to tackle pressing challenges. So again, we're happy to welcome everybody here. Here's a brief rundown of our agenda. So we will just be starting with an update from Scott Hopkins and his team from the University of Waterloo. And then we'll move on to the second part of this project, which is being led by Professor Franco Berruti. And we'll hear from him and his team, and then we'll have some time afterwards to manage Q&A. So we'll go through the content, we'll go through the presenters, and then we'll do the Q&A afterwards. And if you have questions that pop up, either put them in the chat or write them down so you don't forget, and we can get to them during the QA session. And depending on Scott and Franco and your team, if there's a lot of questions and engagement, we purposely ended this at 12:30 so that if people wanted to stay a little bit later and talk to you guys, then I hope they would be welcome to do so. So I think with that, Scott, you're first on the agenda here, and I'll pass it over to you.
Wonderful. Thank you, Rahim. You can hear me?
I can hear you, yes.
And very shortly, you should be able to see my slide deck. Correct?
And we can see it in PowerPoint mode, so not presentation mode.
Good.
There we go.
Yeah. And I'll pull up a...
And I will be a strict timekeeper here too, so I'll let you know when we're running out of time. 10 minutes.
10 minutes, go. Okay. So it is always a pleasure to speak to people about PFAS in Ontario and broadly across Canada. So Rahim did a great job introducing the project. So I won't go into too much detail there. I'll just point out that this is a huge effort between Waterloo, Western, USP, Brown and Caldwell, Aqua, OWC, CWWA, many municipalities. And if I've left any names out here, I apologize. But everybody is pulling in one direction to try to get this problem at least understood, even if we can't solve it immediately. So in today's meeting, here are the friendly faces of the people that are going to speak to you. 6 of us, including yours truly. So on the Waterloo side is Amir and Shannon. and then Franco, Josh, and Asan will take over to talk about some of the treatment aspects that we're developing, which we're supporting with analytical measurements at Waterloo as well. Josh, where are you? You might want to update your picture on LinkedIn because it looks like you're still a graduate here.
That was 3 years ago.
3 years ago. There you go. Okay, so just to remind everyone, PFAS stands for per and polyfluoroalkyl substances. So these are like hydrocarbons in some sense, but instead all the hydrogens are replaced with fluorines. And the thing that's challenging here is there's actually a lot of different chemistry associated with these fluorocarbon chains, which are both good and bad. So the reason why these molecules are everywhere is because they're really great in terms of heat resistance, water resistance. You see uses in food packaging, clothing, nonstick surfaces. The list goes on. The problem, of course, is that now we're starting to find that maybe they're not so good for human health. And you can maybe understand that in the sense that a lot of these molecules look like things that are in your diet. Of course, you have not evolved to metabolize PFAS, though, so that is an issue. We know that they don't break down in the environment. Treatment methods are under development, and you're going to hear more about that later. PFAS can move very easily through soils, contaminate drinking water, and it actually bioaccumulates in fish, wildlife, and humans. Short chain can be metabolized and excreted more quickly than long chain, and for that reason, the longer chain species like perfluorooctanoic acid have been heavily regulated and basically banned from production. And as we're learning more, there are more regulations coming in. So you'll have seen reports from the EPA. Seems like they're coming every 6 months now. In terms of Canada, we had a new objective reported last fall, and we'll tell you a bit more about that. So in terms of the objectives and the timeline that we're working on, we're just past the halfway point of this project. We've got about another year and a bit of work that we're going to do before we get into the report writing side of things. So we're actually getting close to the end. The project itself was looking at developing analytical methods for accurate identification and quantification of PFAS in various different media, along with some development of machine learning methodology so that we could predict PFAS properties and perhaps look at optimizing some processes. Along with the development of new biosolid treatment methods and water treatment methods to see if we could get rid of PFAS in these environments. And in fact, a lot of these objectives are starting to wrap up, are basically in the end game. We still need a little bit more data if we want to build an ML model for process optimization, but we can certainly look at that over the next year or so. In terms of developing a model for PFAS properties, we actually published a nice paper at a Waterloo a couple months ago about this. And proudly, as Amir might not tell you, we've now analyzed almost 1,300 samples that have come through Waterloo so that we can get a handle on what PFAS looks like, both in the research environment, but also out in the real world where municipalities are curious about these things. So our sampling map looks something like this. The blue points that we're highlighting along here are water treatment facilities to produce drinking water for these municipalities. The red flags are wastewater treatment plants. So you can see that we have pretty good coverage-ish of southern Ontario. Certainly along the Great Lakes and out through the St. Lawrence area, we have some good coverage. And over the past couple of years now, we've been monitoring PFAS at these different sites. And again, big thank you to all the municipalities participating. And those folks that did participate have seen graphs that look like this. You've received reports from us highlighting concentrations of various types of PFAS, usually taken weekly over the course of a month. looking at, in this case, drinking water to compare the PFAS levels in the raw water coming into the plant, finished water coming out. So nobody is being revealed here. You can keep that a secret. People who know what this graph is will know it's you that I'm talking about. But you all look the same. The moral of the story is PFAS in is PFAS out. Seems like this is not really being addressed for the most part with water treatment. In some cases, maybe there's a little bit of a reduction. Curiously, in some cases, we actually see an increase in the amount of PFAS coming through the water treatment facilities, and we don't know where that comes from. So what we've done to this point is looking at the input and looking at the output, and we haven't explored anywhere more fine-grained. In terms of what this looks like sort of year over year or season over season, here are 6 of the water treatment facilities. The red line up here is Health Canada's objective for drinking water at 30 nanograms per liter. And you can see that everybody is well under that, so we can all pat ourselves on the back and breathe a sigh of relief that we're drinking good water in terms of Health Canada's objective. A little bit of variability maybe season to season, but not a whole lot. And again, we don't know what that variability comes from. So that's a question. Might it be, I don't know, weather dependent? Maybe we monitored on a rainy day versus a dry period from one sampling session to another. We also should highlight that there are some interferences for some of these molecules. So what we mean by that is there are other molecular compounds in these mixtures that can actually confound some of the results for these. And we're working on solutions to get rid of those interferences. So that's a teaser for the municipalities. We've more or less finished the last round of samples. You're going to get reports coming in the next couple of weeks so that you can see what this looks like from fall 2024 measurements. We've also looked at wastewater. I won't sort of beat this drum more than it has to, but note that the scale is an order of magnitude larger here. And also, here's that PFOSA guy again. In this case, we don't detect any on the way in, and now there's PFOSA appearing on the way out of the wastewater treatment facilities. So that's a curiosity that we want to address. And in terms of what this looks like sort of season over season, here's sort of our bar graph so that you can see the variability over the last year and a bit. A little bit of variability. Again, we need more data if we want to say something about sort of long-term trends here. And this also raises the question now, based on looking at patterns, is there a regional correlation between PFAS concentrations in water and wastewater? Okay, so what's next? On the analytical side, we're continuing our sampling and analysis, supporting research at Western. We're also curious about the origin of this PFOSA, so we're going to dig in a little bit deeper. Big thanks to Greg Barber and the folks at Lorne Park who are allowing us to sample pretty much everywhere along their treatment line so that we can identify the source. We've also started non-targeted analysis. So the targeted stuff we've been doing is looking for a needle in a haystack. Now we're trying to identify all of the needles in a stack of needles and trying to understand what the global chemistry looks like here. And finally, we're developing new analytical and multidimensional separation methods so that we can try to tease out these trace contaminants and quantify them. So you're going to hear more from Shannon and Amir about those analytical aspects. And then Franco and crew from Western will talk about the treatment aspects. And I've gone over by 47 seconds. I apologize, Raheem. I will pass it on.
That was great. Perfect timing. Thanks, Scott. So we have Amir next, and let's see if Amir, you can match your mentor's conciseness here. And if you start going over, I'll raise the virtual hand here, and that'll be your signal to know that you've got to wrap it up. So Amir, if you want to Share your screen.
Getting there. So, hello everyone. Thank you very much for joining this morning. I'm going to go over a bit of non-target analysis and the process that goes into trying to figure out what's else in the sample beyond the 40 or 42 PFAS that we are specifically looking at. So first, I would like to start with acknowledgements. I want to thank all partner municipalities that have been providing samples so far and then plan on participating. Much of what I'm going to talk about wouldn't be possible without those unique samples. The acknowledgements obviously extend to the Waterloo team and everyone who has been helping on this project, and also University of Western Ontario and ICFAR team who have been working on building some cool samples from the pyrolysis or the UV treatment. So over the last year, since last webinar, what we've been mostly focusing on doing more of targeted analysis, going into this fall sampling period, analyzing a couple of samples from Western and ICFAR. But what I'm going to focus on today is going to be about just the development of the non-targeted analysis workflow for PFAS characterization, and going to show a couple of examples on some extracts that we have run so far. So what is non-targeted analysis? It's essentially instead of tuning our instruments to specifically look at compounds or chemicals that we are interested in, we are looking at everything else that is out there. So how this is done in literature is that there are kind of two main approaches. One is that we screen against a list of PFAS. Those lists are can be found online, and they can, or commercially, and they can range from a couple of hundreds, a few hundreds to several thousands. And second way is that we analyze kind of the most intense ions that is present. The instrument is capable of sorting them, and then it kind of breaks them down to look at their fingerprints or fragments. So essentially, with that first method, we are able to, if we got, let's say, 4 ions in our instrument, we can match if they're happening on the list. We can create some fingerprints. But for example, if there is one ion, like this green one on here, it's not on the list, no fingerprint, we are going to miss it. And it's very hard to identify or characterize new PFAS. With the second method, it's a little bit more oriented towards characterizing new stuff. But the thing is that if that ion is not abundant enough, if it's not high intensity, very concentrated, which is the case with PFAS, of what I'm going to show in the next slide, it is not going to get picked up, and we are not going to obtain any fingerprints. So what we have been working on is developing this, what in the liquid chromatography mass spectrometry field is called all ion fragmentation approach. So we let all ions into the instrument and we fragment all of them. So this serves as an initial screening step, where when we generate some of the fragments, we look at some typical fragments specific to PFAS, and then we can log on to those retention times, and we can see what else is there when those compounds elute out of a liquid chromatography column. Yeah, so basically the goal is to develop the method or workflow for identification of new PFAS and the decomposition fragments. So this is total ion chromatogram of a sample of one of the extracts that I've run from one of the samples analyzed so far, and essentially this is how it looks. And when we take one snippet, one time point, we have a spectrum. In this all ion fragmentation approach, we collect one spectrum with low energy, meaning that we are trying to preserve the native species as much as possible. And for example, if we zoom in over here, we can see PFAS, and you can. So I'm keeping everything to the scale how it is, and this small blip over here is what's PFAS. These two over here are some internal standards that are helping us just to quantitate this PFAS, and you can see that how the PFAS originally coming from, let's say, drinking water, or even in some wastewater samples, they'll be really small. And we also can collect another spectrum, which is a high energy spectrum. We're going to apply a lot of energy to start fragmenting these compounds. So we're going to start losing this blip, and we are going to start creating two small ones, which are PFAS specific fragments. And most of the PFAS are designed in such a way that they have very long chains, but the functional groups around them are similar. And we can see those functional groups in some other compounds. We can study how they fragment in the mass spectrometer, so we can develop methods around picking them up more easily. So once we run a lot of samples, we get some candidates of interest. Basically, we need to look at one of the first filters that we apply is about their when we look at their mass to charge, their defect. So these are the most common elements that we come across, let's say, and fluorine for the PFAS. So we can see that the more fluorine the compound has, the more the lower we are going to be below the nominal mass. The nominal mass meaning this number being rounded up to 413. So when we start decreasing the number of PFAS and increasing the number of hydrogens, that number very quickly goes up because of how little decrease fluorine offers compared to how high increase hydrogen gives. And for just octanoic acid, fully saturated, we get a very positive defect. So what we do is we apply a filter of -25 to about +0.1, so we can capture some of these species and also some polyfluorinated species, with smaller degree of fluorination. And when we apply this filter in the, let's say, EPA master list containing 12,000 PFAS, we captured more than 95% of that population. So the thing is that when we have an example of a drinking water extract and a wastewater extract, we can remove about half of the candidates in some cases, so that we don't need to spend those computational resources trying to figure out if that's PFAS or not, which obviously helps a lot. And then after that, we essentially use MS-Dial it's an open source software online, and then we use that software to generate some features. So a feature, as I mentioned here, is a unique combination of mass to charge, retention time, and intensity. And we need to study them to see if they represent PFAS or not. And we get an output that for, let's say, this sample is about 3,000 species or features long. And let's say we are interested in this one that has ID of 1605 in the MS-Dial output. We go to another online resource to try to fit chemical formula to these samples. And then we can have as many as 19 for this one. For some other ones, we can have more. And these are filtered in such a way that they contain at least one fluorine. And if we check PubChem, many of these formulas are not going to have hit because the software is going to think it's just chemically, let's say, many of these suggestions don't make sense. But we get a couple of hits over here, and a dozen of hits here, and then a few dozens over here. And now we need to figure out, are these real? What do they mean? So how do we sort them is that we have this kind of level list, which increases in confidence from level 5 to level 1. And the lowest one is just mass defect, is just indicative of fluorine atoms. If we have isotope pattern of the molecular formula fits. And then here is a space where we have a lot of our candidates, where we have a lot of these circumstantial evidences. But the major bottleneck to push them into a higher confidence level is that we need to have more of the kind of fragment libraries matches, or we match it against a reference standard. So, for example, in these two, I've used these two examples of candidates that we found. In one of them, they're both at level 3. So, but basically, for one of them, we have a very good mass to charge match and chemical formula fitting the isotope and fitting this Kendrick mass defect, CF2 normalized. So this defect is normalized to patterns of CF2, so we can look at homologs in one PFAS family. And basically, these two values being close to each other are indicative that we are probably looking at that family of PFAS. And the same thing over here. But the main issue is that we have one or more structures possible here. For example, this OH if it's here or here or here, or this double one being around, we are not going to be able to discern which one is it. And that's the main bottleneck to how can we go push them into level 2 or level 1. So what, in terms of future directions, what we're going to do is we're at the moment purchasing some analytical reference standards to expand the number of PFAS that we have at hand, to get some high quality spectra that we can fully match and get a lot of fragments for. But again, we're not going to be able to find lots of analytical reference standards for many of the fragments or the composition products or some kind of transformation products in the nature. For that, we're going to be working on building some in silico libraries with some highlighting some fragments from unique functional groups. And also we can use the retention time model, prediction model that Scott mentioned earlier, to increase our confidence on these PFAS fragments to see if that compound can allude to the right retention time. And also we can collect their collision cross-section to get a full fingerprint. That's it from me for today. Thank you very much for your attention.
Okay, super. Thank you, Amir. Next, we have Shannon Lemons, who's a master's student with Scott Hopkins.
Can you guys see my slides okay?
Sure can.
Okay. Good morning, everyone. My name is Shannon, and I am a member of the Hopkins Research Group at University of Waterloo. And today I'm just going to be talking about how we characterize micropollutants in complex environmental samples. But before I start, I just want to say a big thank you to the people that have supported my work. So firstly, a large thank you to Scott, who leads our research group and is constantly providing me with direction and encouragement throughout this project. And I also just want to thank Christian, Arthur, and Chris, who contributed in a bunch of different aspects to this work, anywhere from experimental design to data interpretation. So I'm not going to harp on the same things that Scott's already talked about in terms of why we should care about this project, but essentially the main goal of my research is to separate and isolate micropollutants like PFAS before identifying and quantifying them. This step is really essential for accurate measurements, especially when we're dealing with complex environmental samples. So as we know, micropollutants are a major concern for several reasons, but the main concerns being their extreme persistence, their health risks, widespread contamination, and just the fact that they're very difficult to remove. So overall, we just want to try and up our conventional water treatment methods in order to clean up these contaminants. So we use a targeted LC-MS method for micropollutant analysis, which is currently considered the gold standard technique for detecting known contaminants in complex samples. And during the first step, the LC separates the components of the sample, and that just simplifies the mixture before it enters the mass spec. And then once the analyte enters the mass spec, its exact mass is measured before breaking it apart by colliding it in a gas environment, and usually we use nitrogen. And then those fragments are remeasured by the mass spec, and we use them to confirm the molecule's identity with a high degree of confidence. And then after that, we look at the signal intensities of those fragments to calculate how much of the compound is in our sample. And overall, this entire approach just helps us assure the accuracy in identification and confidence in quantification, especially for trace level contaminants. So when we first looked at perfluorosulfonic acids experimentally, we saw that they consistently fragmented into the same two peaks at 80 and 99 Daltons, which are labeled in green and blue. In the data above, I was specifically looking at perfluoropentane sulfonate and how it behaves under increasing collision energy in the mass spec, just as a case study. So on the left, we have a breakdown curve, which essentially shows how much of each fragment is produced as we increase the energy used to smash the molecule. And the red line is the intact parent molecule. So as we increase the energy, it disappears, and we start to see the two main fragments appear. These correspond to the two distinct chemical pathways. So the green pathway is desulfonation, where the molecule loses a sulfonate group through spontaneous homolytic cleavage. And the blue pathway is defluorination, where we observe the formation of this FSO3- fragment in the spectrum, but the exact mechanism of how this product forms is what's unclear, which is why I've marked it here with a question mark. So the structural diagrams on the right are just there to help show what's going on at a molecular level in each case, and these fragmentation patterns help us understand the chemistry of PFSAs, and they're just a key step forward to confidently identifying and differentiating between PFAS compounds. So in an effort to understand the formation mechanism for the FSO3- product, we decided to use computational chemistry. This helps to give us an idea of the potential energy landscape that we're dealing with. And the reason that this is helpful is because we're really limited in our ability to identify the neutral loss fragments in this mechanism just with our current technology. But this slide shows how I use the NEB method to find the most likely reaction pathway for PFPES. And you can think of it like finding the easiest route over a mountain, where the mountain represents the potential energy surface. And this method maps this out by placing structural images between a starting molecule and a product, and they're connected by these virtual springs that keep them evenly spaced. This approach just helps us understand where and how PFAS molecules might break apart, which is a very valuable insight that helps guide future experimental analysis. So these are two of the lowest energy degradation pathways that I found for PFPES. The top section shows a concerted single-step reaction starting at A. We transition through B to form product C, which includes FSO3- and a terminal alkene, whereas the bottom section shows a non-concerted multi-step reaction that moves through an intermediate structure labeled E before reaching the same final products. The initial ADE transition is actually a structural rearrangement that lowers the energy barrier for FSO3- formation, as you can see on the graphs to the right. And these two pathways have very similar energy barriers, which means that they're both very probable mechanisms for FSO3- formation. But the intermediate from the multi-step pathway is actually a favored starting structure for a few different products, which means that we might actually be getting a mixture of a few different neutral alkenes. But with these computational results, we can really make informed decisions on how to proceed with future experimental studies of these mechanisms. So far, we've just been looking at the gas phase behavior of individual PFAS molecules, and this helps us to understand how they fragment and what patterns we can expect. But in reality, PFAS rarely appear on their own. They're usually found in complex mixtures along with other micropollutants like pharmaceuticals and pesticides. But before we can analyze them using mass spec, we really have to separate them from everything else in the sample. And that's where a 2D separation technique like LC-DMS comes in. And this method has the potential to distinguish micropollutants, especially when they have similar masses or structures. And it just adds another level of confidence in the identification and quantification of these species. So LC-DMS is a two-dimensional separation technique that combines liquid chromatography and differential ion mobility spectrometry. The purpose of LC is to separate compounds in the liquid phase based on how they interact with the column and solvent. And depending on how strongly each compound interacts with the column, they'll exit the column at different retention times, which gives us our first layer of separation. The DMS separates ions in the gas phase based on how their mobility changes under an alternating high and low electric field. And to allow ions to pass through to the detector, a specific compensation voltage must be applied. And this value really depends on an ion's size, shape, and charge distribution, which adds that second layer of separation to this technique. And when used together, LC-DMS helps us to distinguish compounds that might overlap in just one dimension, which is especially useful for environmental samples where molecules might have similar mass or structures. So this work was done by my lab mate, Chris Ryan, who applied LC-DMS to PFAS mixtures, and you may have heard about this last year if you attended. And in this plot, the vertical axis shows the separation by DMS based on an ion's mobility, and the horizontal axis shows the LC retention time. And you can see how this 2D separation method helps resolve compounds that would overlap in either technique alone. So for example, we see 5,3-FTCA and PFHXDA. I can kind of show them right here with my, I don't know if that's working, sorry. And they also 5,3-FTCA and Adona co-elute in DMS, but they are separated in LC. So essentially what this work course, really showed us that this method can effectively separate structurally similar PFAS compounds. And building on that, I just wanted to explore whether LC-DMS could also improve separation of other micropollutants like pharmaceuticals that often have the same similar analytical challenges. So I conducted a study of nearly 40 commonly used pharmaceuticals and separated them into 3 batches. And this is one of those batches where I tested the separating power of each technique individually to see if there were in fact co-eluting species, and that was what we saw. So you can see in the top plot we have DMS separation, and compounds like bisoprolol and lansoprazole, which overlap in the LC space, are clearly resolved based on their compensation voltages, whereas the bottom plot shows LC retention time, and compounds like econazole and meconazole, which are co-eluting in the DMS space, are successfully separated here using chromatography. So by combining both dimensions, LC-DMS might provide a clearer separation than either technique alone, and this just demonstrates its potential for analyzing pharmaceutical mixtures, especially when compounds are structurally similar or present at low levels as well. So here is a 3D LC-DMS plot showing the separation of these pharmaceutical compounds and their corresponding intensities. And you can see those examples like bisoprolol and lansoprazole, which are separated by DMS despite being very close in retention time. And similarly, econazole and meconazole are clearly resolved by LC, even though they have very similar compensation voltages. So this plot just reinforces how using both separation dimensions really improves our ability to distinguish these compounds that might overlap otherwise. And that's really important, especially when we're looking at complex mixtures. So just to summarize, there's several ways to build on this work and continue improving micropollutant analysis. For PFAS, future work will really focus on validating our computational predictions with techniques such as IR spectroscopy and studying how solvent conditions might affect fragmentation behavior, and gaining these insights for both short and long-term PFAS. PFAS will really help support mitigation strategies to limit the environmental and health impacts. And also on the pharmaceutical side, applying LC-DMS is really good for real sample matrices like wastewater, and it's a key next step to helping with qualitative screening, and quantitative workflows will also really be improved with monitoring these contaminants. And just finally, expanding our target compound database will allow us to investigate retention and mobility trends across different drug classes, which could also lead to more predictive and efficient screening strategies. So thank you for your attention. I really hope this gave you a clearer picture of how we can combine experimental and computational tools to help improve how we look at micropollutants like PFAS and pharmaceuticals.
Super. Thank you, Shannon. And thank you, Scott, and your whole team for giving us that walkthrough, that update on the progress on the analytical side of this project. And so now Professor Franco Berruti from Western University and his team will walk us through the progress on the treatment side of this project. So Franco, over to you.
Thank you. Let me see if I can go in the, I don't, for some reason it doesn't go in presentation mode.
There you go.
Yeah. Okay, thank you for the introduction. Today I want to give a quick overview on the technology that we have been using at Western for dealing with the treatment of biosolids that are contaminated with PFAS. Josh later is going to talk about the experimental work that we are doing, conducting here at Western, but my task here is to talk more about the technology itself and how it could be implemented at the commercial scale. So the vision that we have is that we want to develop a pyrolysis technology. Pyrolysis is the process that we are using for thermally treating the biosolids and displacing the PFAS molecules into the vapor and the gas phase, where then they are treated further with thermal oxidation to go to high temperature and fragment further. So the objective, our vision is to develop a pyrolysis technology and move it from the pilot to the commercial scale to deal with the conversion of biomass. And we talk about generally biomass feedstocks, but specifically biosolids here, into a biochar that will be free of the contaminants, and followed by the combustion of the vapor and the gases that are produced during the pyrolysis process for recovering the energy for the process itself to make it self-sustained from a thermal standpoint and take care of the thermal oxidation of the contaminants that have been moved to the vapor and the gas. We started this with the development of the technology with an investigation on what is possible. Can we develop a self-energized pyrolysis process for producing a biochar that will be free of contaminants and make it self-energized by combustion of the vapors and the gases, combustion that will achieve two objectives. One is to generate the energy for the process. The second is to thermally oxidize the contaminants. The study indicated that indeed it is possible, and the combustion of gases and vapor products of feedstocks that are sufficiently dry generate sufficient energy to self-sustain the process. And we looked at the parameters that are important, that are affecting the process itself, and published this paper which summarizes the results. The principles of the process are the following. We have a pyrolysis reactor where the feedstock is introduced after a drying process. We know that biosolids are wet, and many biomasses in general contain moisture. Therefore, we have integrated in our pyrolysis process also a drying process. So the wet biomass, the wet feedstock, goes into the dryer, and then once it's dry, goes through the pyrolysis reactor. The pyrolysis reactor generates vapors and gases and solids. The solids are extracted in the form of biochar. The vapors and the gases go to a burner where, mixed with air, they are combusted and they generate the energy for the process itself. So the reactor is heated up by the combustion of these vapors and gases, but extra energy remains in the flue gas, which then goes into the dryer and provides the energy that is required to dry the feedstock in the first place. After going through the dryer, the flue gases now are cleaned from any dust, and there may be still additional energy that can be recovered before going to the exhaust. The objective is to create a process that is self-energized from an energy standpoint. This is our pilot plant, our larger pilot plant that has inspired the further development of the technology to the commercial scale. It's a reactor where the feedstock is entering the reactor, and it enters a bed of biochar that is very mixed very efficiently. Particle to particle contact provide good heat transfer. Eventually the product is overflowing over a weir and being separated, whereas the gases and vapors are filtered through a hot filter inside the reactor. They go to a combustor, a thermal oxidizer, where they are mixed with air. They generate the energy for the process that is then providing the heat that is supplied around the reactor itself before going to the flue gas exit. This reactor is called pyro. We call it pyro because it's a pyrolysis rotating horizontal reactor. The key features are that it's relatively simple. We have tested this technology and we have optimized the design over the years. It's energy self-sustaining through the recirculation and combustion of pyrolysis gases and vapors, which removes all the complexities of handling condensable vapors into bio-oils, and which typically create a product that is of low value, and tars and plugging and so forth. Very important in this case, it's the thermal oxidation and destruction of the contaminants, specifically of the PFAS. And the excess energy allows for the drying of the wetter biomass, and additional energy can be utilized to produce other things like steam. This is a novel reactor design which provides optimal mixing, high transfer, both from the external surfaces to the reactor, as well as the particle-to-particle heat transfer inside the reactor between the bed of biochar and the fresh incoming feedstock. We have a long residence time of the solids so that they get fully converted, and therefore we end up with a homogeneous, stable, and the PFAS-free biochar. Now we decided to go to the next level, and we took our technology to the commercial level. And we created a spin-off company called ITER. We teamed up with a company called JCT in Colombia, and jointly we developed a technology that has a processing capacity of about 2.5 tons per day of feedstock, fully automated. We have commissioned the unit, we have tested it. It's very successful, and it's working very well. It's called Valentina. And we have gone to the next level, which is a further scale up with the integration with the dryer. This is only designed at this stage. We haven't built one yet. It has a processing capacity of 1.2 tons per hour. It has an integrated dryer system, and it's also fully automated. There is competition. We are not the only people that are in this business of pyrolyzing biosolids to make them PFAS-free and thermal oxidizing vapors and gases. We have seen recently the announcement of Sinagro and Chartec that have been doing some demonstration testing with a unit that is actually smaller than our Valentina, and different technology. We trust very much our own technology. We believe that it is superior, and we want to prove this in the near future when we can implement this with our partners. So thank you very much for listening.
Okay, super. Thank you, Franco. So next is Joshua Cullen, who's Franco's PhD student at Western. Joshua, you are up.
Okay, you guys can hear me all right?
We can hear you and we can see your slides.
Okay, perfect. Okay, good morning, everyone. My name is Josh. I'm a PhD student working under Dr. Berruti and Dr. Klinghoffer over here at Western. And today I'd like to give a little bit of a review, a refresher from last year's webinar, some updates over the past year since then, as well as some information on the direction of our future work, which is focused on destroying PFAS and capturing fluorine from PFAS from biosolids using pyrolysis and thermal oxidation technologies. So to give a quick summary, our work boils down to a few different things. It centers around conducting experiments with our thermal treatment system, BEVEC. In that workflow, we focused on processing and characterizing some of the biosolids that we receive from different sources around Ontario and the United States. We focused heavily on implementing improved sampling methods for identifying PFAS and PFAS byproducts from our system's effluents. And we've also done some work treating PFAS contaminated biosolids, evaluating different treatment conditions, potentially using additives, changing some of the units within our system. So when we talk about PFAS treatment using specific first pyrolysis, the main goal essentially is to produce PFAS-free biochar. And at last year's webinar, I presented some data from some previous pyrolysis tests that we did in collaboration with the team at Waterloo. And we were able to do targeted analysis of the biosolids before treatment, and then targeted analysis of the products following treatment, so the biochar and condensed vapor phase or the bio-oil. And essentially what we reported from last year was a significant reduction in measurable or detectable PFAS within the biochar. However, there was still a fraction of detectable PFAS within the condensed vapor phase or the bio-oil. And so what this means for PFAS treatment using pyrolysis essentially is displacement of PFAS from the solids, but they remain as PFAS or potentially alternate forms of PFAS in the gases and vapors. So that is why it's commonly proposed, or one of the reasons why it's commonly proposed, that thermal oxidation be coupled with these pyrolysis technologies, essentially reacting the volatiles or vapors and gases from pyrolysis with air at high temperatures in order to treat the volatile PFAS emitted from pyrolysis. And so at the end of last year, we published a study, which can be summarized by this PFAS flow diagram of our system. We loaded PFAS contaminated dry biosolids, pyrolyze them, collect the biochar, and then treat the vapors and gases at high temperatures in our thermal oxidizer. And we essentially did target analysis of the inputs of the air to the thermal oxidizer, the biosolids into the pyrolysis reactor, and then the outputs of the biochar and the flue gas. But really the main headline data point for this paper was a significant reduction in the measurable PFAS in the flue gas to less than 0.2 mol% of what was initially measured in the biosolids. And so what this really means for successful thermal treatment at this point of PFAS, or what is typically referred to as an effective destruction and removal efficiency, is the displacement of PFAS coupled with either fragmentation into shorter chain volatile fluorocarbon byproducts, or potentially some kind of transformation of the PFAS, both ending up out of scope for our current analysis. So that is why one of the reasons we've heavily focused on flue gas or improved flue gas emission sampling. So we've been developing two in-house methods based on the OTMs or other test methods outlined by the US EPA, OTM 45, which is essentially a series of PFAS filtering media filters, sorbents, and water bubblers for target analysis of 40 to 50 PFAS analytes. These are your classic perfluorocarboxylic acids, sulfonic acids, etc. And then also OTM 50, which is analysis of the potential byproducts of PFAS as a result of thermal treatment. So essentially those fragmented, shorter chain fluorocarbons. So what this allows us to do essentially is cast a wider net on what is produced from thermal treatment to try and address some of the missing fluorine that we see once we report target analysis of essentially destruction of PFAS. So that is one way we've been improving our system. But the other way to address the missing fluorine is exploring a different treatment path, which is essentially using metals for mineralization of PFAS. So including metals such as calcium or magnesium to try and form inert fluoride minerals. So some of the additives we've been looking at are oxides and hydroxides of magnesium and calcium. But based on our characterization and initial testing with some additives with biosolids that we did in the past, we also saw that biosolids themselves inherently contained a lot of calcium. So that led us to do a review of what form of minerals, specifically focusing on calcium, are in different biosolids. So for example, I've highlighted the minerals of interest, folded them. Look at China, the calcium that was reported in the minerals are in large whitlockite and elvite minerals. But however, say in the US, there's calcite, Argentina calcite that was reported. In Turkey, forms of calcium sulfates. Places in Europe had oxides, hydroxides, and sulfates. And then actually looking at our own samples, which we have been working with, basanite, calcium sulfate, and also essentially kind of what we put together for all the ones in Ontario also showed basanite or calcium sulfate. And so what this really highlights is that for the basis of pyrolysis or thermal oxidation, it might change depending on the composition of your biosolid ash if you have these reactive minerals. So, and we kind of showed that when we looked at our biosolids that we've been working with no metal additives, but spiked with PFAS and PFAS precursors. And we're able to verify the reactivity of some of these minerals. So for example, looking at this microscopic image of California biosolids showing with elemental maps calcium and sulfur, calcium in pink and sulfur in green. Following thermal treatment, we can see the displacement of sulfur on the sites of calcium, and instead the formation of calcium fluoride minerals, fluorine in blue, really this captured fluorine. And so now this really ties into our current workflow where we're doing pyrolysis tests with various Ontario biosolids, looking at different solid residence times, temperatures, and additive loading. So essentially we're looking at different loading of calcium hydroxide. And we want to incorporate now our new PFAS emission sampling systems for OTM45 and OTM50. And what we would like to do in the future is to compare the effectiveness of metal addition from our testing with pyrolysis and evaluate the most effective method based on maybe including metals with thermal oxidation or potentially downstream in some kind of scrubber form. And finally, based on the conditions that we investigate for removing or mineralizing PFAS from biosolids, we want to evaluate the possible applications of the biochar based on its properties and composition. So that is pretty much a review of our current state of our work. And I would also like to thank all the supporters and collaborators for this project's progress and funding, especially the Waterloo team, because this would not be possible without them. So thank you.
Super. Thank you, Josh. Next, last but not least, Ehsan, who's a PhD student of Franco's. Give us an update on an integrated vacuum UV treatment system. So we can see you. And your slides are coming up.
Hear me as well?
And we can hear you, I think.
In the slides?
Yeah, we can see your slides.
Perfect. Hello, everyone. I'm Ehsan, PhD student at Western University, and I'm working on addressing compounds of emerging concerns such as pharmaceutical and PFAS from water using a membrane vacuum UV treatment system. So before continue, I just want to mention what was our incentive to start this project. As you know, right now, due to the water scarcity, historical overallocation, or the climate change, accessing to the clean water is going to be challenging every day. So going towards the reusing the water, such as the approaches like One Water, is going to be inevitable in the near future. But if you go through that step, the first thing that you may face with it is that the compounds of emerging concerns, these are like herbicides, pharmaceuticals, PFAS, that we entered into the water. We introduced them into the water in the past decades. And most of them share the same characteristics, such as the low concentration, hard to treat, and our conventional water and wastewater treatment, as mentioned before by our team, is either ineffective or insufficient to address them completely. So one of the configuration that currently we have is the full advanced treatment, which is so effective to have a clean potable water, which is contain a micro or ultra filtration to remove suspended solid to help our high pressure membranes such as RO, and then send the permeate water, the clean one, to the advanced oxidation processes. But here, as you can see, there's a problem is that side stream, which is fully concentrated with the original contamination that we actually built this facility. And in most cases, after some environmental safeties, they send it to the ocean. And this itself is one of the limitations of using such a facilities. As you can see, the recycled water locations around the globe, most of them are located in the coastal areas because of one of the reasons is this limitation. So if we go back again to that full advanced treatment, you can see a couple of challenges that we are dealing with. First of all, the reverse osmosis system, based on the water sources or number of trains that you use, you have a limited recovery. On the other hand, for the advanced oxidation process, right now you can find on an industrial scale the RO systems that can reject almost most of the organics that you want to removed from the system. But you have, in that case, you have to deal with the very low concentration of the organics in a very high volume. So you need a high dose of UV. That means a high capital. And also, as I said, the brine management is going to be challenging. So what if we put that advanced oxidation process on the brine side? So in that case, if we run our reverse osmosis on the higher recoveries, which I'm going to get to that point in the later, we can deal with the low volume with extremely high concentration of target chemicals. In that case, we are not going to be just limited for the coastal areas, and also we can meet the environmental concern as well when we dispose the brine into the environment. But the problem again is going to say, as I said, if we use a reverse osmosis as some sort of a technique to uncouple two soluble fraction and send the target chemical to the brine side, we have to deal with the highly concentrated stream. So we need a high dose of UV again, and this is where we should go through the process intensification techniques. The one we have here is the recirculation. It means that after the uncoupling that chemical and send it to the degradation, we can recirculate back to the inlet and do this over and over and trap the target chemical inside the system to get the full mineralization and make sure that the water comes out is going to be safe. So based on this idea, we built this pilot that is currently running at ICFAR. And as you can see, we have the reverse osmosis membrane, which is the brine of it goes to the VUV vacuum ultraviolet system. Why we are using the VUV? Because we believe that we can use this system to degrade the target chemical, target contamination chemical free. And instead of adding the hydrogen peroxide with the ultraviolet, we can do it by the VUV, which is going to photolysis the water itself for us and also make the hydrated electrons. So in controlling condition, we can either have advanced oxidation or reduction processes. And also we tested this by with PFOA, and as you can see, VUV could itself chemical-free degrade the PFOA. But the problem is coming from the non-targeted analysis. And as you can see, the C8 is degrade over time. We have a bunch of C5, C6, and C7 byproducts increasing. This itself shows why we should the recirculation inside the system to trap these chemicals to make sure that they're not only the target chemical, but also the byproduct is going to be degraded. So to test our hypothesis, to see how our system works in this condition, we chose 4 pharmaceuticals. And we compare our system, the ROVUV system, with 2 benchmark the systems that are currently running on the water treatment facilities. We compare it with the just rejection with RO, and also we compare it with just degradation. So as you can see, I just want to say summarize our results, but by comparing the permeate, the clean water coming from the ROVUV system gives us a cleaner permeate. And this is because in each cycle, we degrade part of the pharmaceuticals. And when they enter the RO, we actually help the rejection efficiency of our membranes. On the other hand, the problem that I mentioned earlier is the retentate, the concentrated stream of the reverse osmosis, which is the problematic. But in our case, by putting the VUV in our cycle, the retentate concentration was for 2 of our pharmaceuticals, the acetaminophen and sulfametrazole, was the same as the contaminated water in the beginning. I mean, after 10 times of concentration, there is no increase in the acetaminophen and sulfametrazole concentration. This is because of having the degradation inline in the system. And for the other 2 pharmaceutical, the concentration was much lower than the salt separation with RO. And also the degradation side. Because of having the RO before VUV, we actually pre-concentrated our pharmaceutical. And that, again, gives us the higher degradation efficiency. And finally, we compare the electrical cost of the treatment of these 3 systems. And as you can see here, even we have a high pressure pump, we have a lower electrical cost of treatment in comparison to the VUV. The EO was lower than just having a lamp. So for the next step, right now we are currently studying the effects of this, our pilot, in degrading tree for PFASs from CH6, from sulfonic and carboxylic acid, from different target concentration. Our challenge is going to be the water matrix of the retentate. Each different membranes, the RO or NF from different, from loose to tight modes, is going to be, gives us a different water matrix, which is going to be interfere in our degradation, which can be scavenging effect or going to be photosensitizing effect. And we are going to study this in the near future. And I just want to mention that in this research, we are not alone. We have different partners from the academic and industrial side, and I just want to thank all of them. Thank you so much.
Super, thank you, SN, and we're almost right on time. So I'm just going to invite Franco and Scott to, and your teams, the rest of the presenters, to come back online, turn on your cameras if you can. And then we can open up the floor to questions, and I'm happy to kick it off. Maybe a question to Scott and Franco here. Can you just remind us how much time is left in your project? Is it one more year? And then are you planning for kind of the next round? What's coming next to keep the work going? That's kind of question number one from me. But then also, can you talk a little bit about like, are you hitting the objectives that you laid out in your original proposal? Are you getting to those milestones, and are there any challenges, you know, if you want to talk about ones that you've already overcome, but are there any open challenges right now that you have that perhaps somebody on this, you know, call might be able to help with?
Okay. Shall I? Yeah. First question first is the timeline. So the grant will officially end in 2 years. So in terms of the research that we can do, I would say we've got another 18 months of effective research, and then we're talking about wrapping up, because at that point it's thesis writing, paper writing, report writing, that sort of thing. The objectives we're checking off. I showed you a table of those objectives, and it was mostly green arrows all the way down through. When it comes to developing optimization AIs, that becomes very data dependent, and we need more data in order to do things. So there are some strategies that we've been looking at on the Waterloo side, tangential to this research, based around the idea of transfer learning, where you learn on one thing and then transfer that information to an entirely different side of the tracks. So that could be something that we could investigate as well as we continue to build up our data. But the frameworks are in place as far as the AI goes. All the analytical methods are in place. We've developed separation techniques. Franco is done incredible work with the pyrolysis side and is actually commercializing things at this point. So that's incredibly exciting. And you just heard from Hassan about the incredible work they're doing. So we're certainly on target. Was there a third question in there?
Yeah, just are there any you know, major challenges that you've overcome so far? But maybe more important, are there any like open challenges that maybe someone on this call maybe could help you with?
Yes. So there are lots of challenges in all of this. So I'll allow Josh, Hassan, and Franco to talk about the challenges they've had. On our side, some of the sample matrices that we get are bonkers. they're really hard to deal with, especially things that are really heterogeneous and greasy, and things along those lines have been tough. There's also a challenge with regard to the non-targeted side of things that Amir is working on. So once we've got a handle on targeting sort of the usual suspects, We sort of opened our viewport to see what else is in these samples, and oh man, are they ever complex? And it turns out that, I don't know, 90%, maybe more of the signals that we're seeing, we can't identify. We have no idea what those molecules are. So, if you're trying to get a handle on the chemistry that's happening, and you don't know what 90% of the molecules are in your chemical sample, it's a real challenge. And of course, another one that I highlighted right off the start was the fact that we're seeing one particular kind of PFAS, PFOSA, actually be generated during the treatment processes, or be introduced. I shouldn't say generated, it could be introduced somewhere. So that's an open question that we really want to address as well, is to identify what reaction is making that, or what addition is introducing that in the treatment process. But yeah, I'll hand over to the other guys for comment.
Yeah, no, from our point of view, at least on the pyrolysis side, we are really good in displacing the challenges to you people, which is we create samples, and then you have the challenge to deal with their characterization. Now, I guess from our point of view, we have made a lot of progress, and we are really pleased with the developments. I think in some areas we have gone actually beyond already what we had originally proposed. But we are also very happy about the steps towards commercialization, which is, at the end, we want to be able to offer to our partners an opportunity to actually implement this. And as I was showing in my presentation, we are not the only ones that are looking at this technology of pyrolysis and thermal oxidation. And what we want to do is to understand it very well, to be able to offer a technology that is really competitive.
Okay. All right. Thank you. Thank you both. If there's any other comments from the team, but for some reason my Teams is not opening the chat window, so we're just going to do Q&A here by raising hands and unmuting people. So Angela, I see your hand is up, so go ahead.
Hi there. That was excellent. I enjoyed all the presentations. Thank you so much. I think this question is maybe directed to Scott. So I registered the comments about PFAS not decreasing, but maybe increasing at water treatment plants, drinking water treatment plants. But in wastewater treatment plants, like I observed that the order of magnitude of PFAS it's an order of magnitude higher. It's like 100 to 300 nanograms per liter. What's the difference between the influent and the effluent?
In terms of the wastewater,
Yes.
Effluent is significantly lower in the wastewater treatment plants. We think that a lot of the PFAS is actually being locked up in organics in some of the solids that are being filtered out. There's also, I can't remember the exact term that Greg used, but it's basically like a slurry foam kind of thing that will develop in some places. That I think is also pretty high in PFAS content. So in terms of in versus out, globally, we don't see a lot of treatment, but in terms of the effluent water, it's substantially reduced, which is a good thing, obviously.
Okay, so it's showing up in the solids and the slurry, the foamy slurry that you're talking about.
Yeah.
Yeah. Super. Thank you.
You're welcome.
Thanks, Angela. Any other questions?
Indra had a question. He says, Scott, how can the learning be transferred to small communities and First Nations?
Small communities and First Nations, we will actually write some reports. The webinars are going to be also broadcast. We've started interacting with the First Nations community in Brantford area, which is part of actually 2 different NSERC Alliance grants now, which is exciting. And we're very much open to conversation. So, you know, if people come toward us and say, hey, we're really concerned about this in our area, then we're more than happy to talk and maybe even run a sample or 2 to try to give you some idea of what's there.
Thanks for sharing that, Angela. You're now my co-facilitator for questions because I can't see the chat. Is there anything else in the chat there, Angela? I see some hands up. No,
I can open
now. Okay, let's go to Benoit. Benoit, I think you've got your hand up first here.
Yeah.
Benoit, then Rob Holler, and then Farouk.
Great. Thank you for making this webinar available. Great presentation, great work from everybody. It's interesting. I'm with the Ministry of Agriculture, Food and Agribusiness, specializing in biosolid non-ag source material and application, and interested to a bit more information on the pyrolysis process and how cost effective it is. And so there was some references of 1 to 2 tons per hour. Are those on a wet ton? Like what is the I guess the dry content of the material going into the pyrolysis unit, and at what concentration of PFAS does it make sense, or that I guess the pyrolysis and the thermal oxidation of the vapor is effective or optimum?
Okay, the scale of the technology, when we refer to the processing capacity, we are referring to the wet concentrations. In fact, the large-scale unit that is designed, not built yet, has the dryer integrated. So we have the removal of the moisture in the dryer, and then the processing in the pyrolysis process. As far as the concentrations, I'm not sure. We have used the real samples, so we have been processing samples that are coming to us from the partnership here in this project, as well as we are processing samples coming from the US as part of additional projects. We intend to do some testing also by spiking the samples. We believe that the residence times in the pyrolysis process are sufficiently high to displace from the biosolids the PFAS molecules and fragment them to some extent very efficiently, independent of their concentration. When it comes to the displaced fragments and molecules in the gas and the vapor, we have done testing, as I said, based on the actual samples that were provided, and with sufficiently high temperatures, which means around 900, 1,000 degrees Celsius, and residence times in the thermal oxidizer of the order of at least 2 seconds, we have seen basically a complete reduction of the detectable PFAS. All this can be further optimized based on the samples or the material that needs to be processed. The pyrolysis systems are very versatile, and we can play with the operating conditions like residence times and temperatures to accommodate different situations.
All right. So I take it that the biosolid or the sludge coming into the dryer was around 20-25% solid.
We need to reduce the moisture content coming into the pyrolysis system to levels below 20% to reduce the amount of water that is then vaporized in the unit, uptaking energy and generating dilution of the calorific value of the gases and vapors that then need to be combusted. So we need to reduce the moisture content to levels below 20% at the exit of the dryer, at the input of the pyrolysis unit. Input to the dryer can be much wetter, and it's only a matter of sizing the dryer accordingly. We have plenty of energy.
Okay, thank you.
Thank you. Farouk, you're next, but Rob Holler, you had your hand up and now it's not, so I'm not sure if that was a mistake or not, but Farouk, go ahead.
No, it definitely wasn't a mistake. Can you guys hear me?
Yeah, we can hear you.
Okay, awesome. I first of all, hey Angela, I wanted to say a huge thanks to these teams for doing such a great work. Being in industry and working in this topic, I know how much great work you guys are doing, especially not having a lot of directions with some of the complicated samples that you guys deal with. It's just kudos. I know, Scott, I know, Franco, what you guys are going through. So thank you so much for that. And I had one suggestion and one question. So my suggestion was that for that foam sample that you talked about, Scott, that we have also seen a lot of those foams coming as an issue and really nicely concentrated in the treatment plants that maybe in future, if you're looking at the treatment technologies, that could be something that you want to look at how to treat that stream that's ready, that's concentrated, and do something about that. So it's really a great area to focus on. So that was the suggestion, and happy to talk more on that, how to develop on that. And the question was around the wastewater treatment plant. I was just curious, sorry if I missed it, if you mentioned if they were all municipal or they were also industrial treatment plants as well, because I'm pretty sure it's going to be a significant difference between the industrial and the municipal treatment plants.
I think there will be a significant difference. I don't remember if we have an industrial in. I think it's just municipals, right?
That's what
I'm looking at Larry. He's brain 2.0 for me. So yeah, so it's all municipal that we have in the project right now. It would be very interesting to have some sort of industrial treatment plant to look at.
For sure. Great. Thank you so much. Okay.
Thank you. Okay, Annie, and then Rob Holler, you're back. So we'll do Annie first and then Rob. We cannot hear you.
Cannot hear you.
Can you hear me now?
We can.
Yes, successful.
Thank you so much for this great presentation. My question is around the pyrolysis. I just want to ask, are there means of measuring like how much of PFAS is converted into like the vapor form? And what I'm trying to get at is to say, okay, this was the amount of PFAS, or these are the ranges of PFAS compounds that were present before. And during pyrolysis, if anyone was converted to vapor form before any crystallization and stuff like that, just to have a closed loop of if there's any loss anywhere. And yeah, I just want to know if there are transformations while doing the pyrolysis and the amount of PFAS that was transformed to which other forms are available.
Yes, in fact, we did, and we are doing experiments where we are not sending the vapors to the thermal oxidation, but we are condensing them into bio-oil. And then we pass on the challenge to our friends in Waterloo to deal with the bio-oil and characterize the PFAS that are in the vapor. So that's the way to see what has happened from the initial contamination in the biosolids, what has been transferred in the vapor phase. We are doing it by characterizing the condensate.
Right, thank you.
Okay, thank you. Rob Holler.
Yeah, I'm back. I put my hand up, but then Angela and Benoit got into the biosolids questions. But just to maybe clarify, so the on Angela's question, we know the PFAS influent, we know the PFAS effluent. So I assume the rest is now in the biosolids. Are there any data collection shareability of what we're assuming the PFAS levels are in the biosolids pre-treatment? So I know you're looking at treatment, but right now at all these plants pre-treatment, do we have a sense of the PFAS still remaining in the biosolids? And I expect Benoit would want to know that kind of stuff too.
We do have a sense of that. We've measured these separately and done some extraction for these. Do you remember concentration levels, Amir? For
Not from top of my head,
but hundreds.
Yeah, they're very concentrated.
Yeah, this is quite concentrated. Hundreds of nanograms per kilogram is what you see in the biosolids. The foams about the same, I would say.
Without,
I'm putting Amir on the spot to recall numbers like that, but
I can comment on the fold. The folds would be in the magnitude of thousands.
Oh, is it? Okay.
Yeah. Without compromising, who your people are. Sorry. Without compromising, your sources. Are you able to share any of that with me?
Yeah, we can share some of that. We've got a paper under review, back from review, going to go again pretty soon to report on some of this. But if you're looking for really fine details, Rob, write me an email. Let me know exactly what you want, and I can deliver some numbers to you, holding back names probably, just so that we don't put anything out there. But absolutely, you're free to have that.
Yeah, I'm being asked to put out a statement that the benefits of biosolids are great and the PFAS levels are so low, nothing to worry about. And I just want to know if they are truly still so low in Canada, or is it something that I got to stop saying? Yeah.
Let's talk. I think. Yeah. I don't want to. Yeah.
Exactly. Thanks.
All right. Thank you. Back to you, Benoit.
Yeah, I guess just a comment. Of course, Robert, I would be interested in knowing that information. I guess from Environment Canada and other federal agencies, it seems like the PFAS or the P4, PFOS concentration are relatively low. So I'm wondering if the references here, the number that are being mentioned in the thousands are total PFAS or just single one. I assume it's total PFAS. But, a lot of jurisdictions in the States have shown that source control does reduce significantly PFAS concentration. So I'm wondering if there's been work trying to, apply the technology to more concentrated sources to eliminate, before they're being discharged into the sewer. So industrial application or landfill, municipal landfill type of thing.
Can I volley that over to you, Franco? We haven't done anything like that. It's certainly something that's on the horizon. We've had conversations surrounding that sort of idea, but nothing implemented as far as we've done yet.
Same here. Yeah.
All right. Thank you.
It's a time and money problem.
Yeah.
Okay, well, I'm not seeing any other hands, and we've just about hit our 12:30 limit here. So thank you to everybody for joining us. Scott and Franco and team, maybe you want to stick around for a couple more minutes in case questions pop into somebody's head here. But thank you to everyone for joining us. We're looking forward to continuing to keep track of the progress of this exciting project and continue to help disseminate the results and good work that this team is doing. So again, thanks to all the presenters, and then hopefully we'll see you again soon.
Thank you. Great presentation.
Right. Thanks all.
Thank you.
I see it was Indra that asked the question in the chat here. Indra, how are you? He's one of the prime movers from this project. I don't know if he's still on the line.
Maybe
not.
No, don't see him. Yeah, sorry, I don't know what happened to my chat here. It just it won't load in Teams, but if that was the only chat question, then not a big deal.
I think I have some of the emails, but maybe if Rahim, if you can make sure I get connected to everybody, and I'll formulate my question a little better.
To Scott. I mean, we can reconnect you.
Thanks. Okay, guys, take care. Thanks a lot. I'm happy to be supporting on this, and at some point may talk about a national webinar again through CWWA or at our coming events. I'd like to stay on top and share some more of this. So thanks.
Yeah, that'd be great. Always a pleasure.
Take care, guys.
Thanks, Rob. Cheers.
All right. Bye.
Can I
Okay.
meet you guys for 1 second?
Hi, Farouk.
I guess just the project team members, if nobody else has a question. So I'm just impressed by the great work that everybody has done. And I think it's going to be such a waste if we don't showcase this work as this is wrapping up and there's a lot of great things coming together. And what I wanted to suggest was to get our Brown and Caldwell marketing help and see how we can disseminate this information and talk about it more broadly in the industry and in our company, first internally in our company, because we're doing a lot of PFAS work and research work. And it's going to be really great for everybody to know. And I don't think we are there in terms of visibility of this work. Like, even I'm going to be frank with you guys, like, I'm supposedly I'm the project manager for this project, and I didn't know everything because I wasn't doing a great job of coming to all the meetings. But anyways, so I wanted to talk more on how we can get that out there. Maybe we could start with collecting the articles that we have published so far, and have like links to those, and create a plus social media campaign and the blog on our website, on Brown and Caldwell website, to make sure that the word get out there. Of course, I know that data is sensitive, and we may not want to like release all the names, but even anonymously, even to talk about what we have done, the great technologies that Franco, you're working, and the awesome results that Scott, your team got for the treatment plans. So let's maybe put this as an agenda item for our meeting that, Scott, you have sent to us, so we can talk more about it. And obviously we'll love to get, Rahim, your help, because you guys are great in disseminating information as well. So yeah, just wanted to put it out there that I think this great work need more ears and eyes to see. That's it.
Happy to help with that however we can. So I think it's next Thursday that we have our regular monthly update. So yeah, let's make that a talking point for next week.
That sounds great. Okay. And thank you. Okay. I'm going to drop off now.
Have a good day.
Thanks. Thank you.
Thanks. Bye.
Okay. All right, Scott and Franco and team. I think that wraps it up. There's 9 people left, so great job. That was really good. I think we had great flow and kept things going, and there was some good engagement. So